So this leads me to the introduction of our first speaker today, who is Jean-Michel Morel, professor at Ecole Normale Supérieure Paris-Saclay in France, where he leads a team of 20 researchers and coordinates 20 more on the mathematical analysis of image processing and the invention of new algorithms. Among many achievements that Jean-Michel has made, his team collaborates with the French Space Agency for the design of Earth observation satellites such as Spot 5 or Pleiades. Their image denoising algorithms are implemented in more than 300 million camera phones by DxO Labs, and Jean-Michel has been the founder of Image Processing Online, which some of you know as IPOL, which is the first journal really publishing reproducible algorithms in an online executable format with demos and a really comprehensive documentation of these algorithms. Is something that all of us researchers in mathematics for image processing have appreciated very, very much that he has started this and is still carrying on with his team on this. It's a great resource. As a mathematician growing up on the mathematics for image processing myself, I encountered Jean-Michel also for the first time for his axiomatic theory of image analysis, which had and still has a great impact on the field, and his foundational works on image denoising and image impainting, just to name a few. For his achievements, Jean-Michel has been awarded with several awards and honors, among them the 2010 Clay Scholar in Residence, an ERC Advanced Grant in 2010, and the Grand Prix INRIA award from the French Academy of Science in 2013. So without further ado, I hand over to Jean-Michel, who is speaking to us today about research on the synthesis of the forms and abstract images.
Thank you, Carola, for the nice introduction. It looks too good to be true. So, since you talked about IPOL, I would like to say that we are not satisfied the way IPOL is running, because we think that it takes too much time to go from submission to publication, and that we are demanding too much to the authors. So we are considering allowing authors to publish notebooks directly, like Jupyter notebooks. Okay, so that would be, because we see that more and more people in machine learning are using notebooks, and so it's what's called literate programming. So that means annotated programming, which is fine and much easier probably to review than what we ask today. So probably this will, we hope this will get us to receive more submissions. So, okay, so do you see my screen here?
Yes, we can see it.
Okay. Yeah, so you asked me to talk about something that I have been working with Luis Alvarez for many years. We both are mathematicians, so somehow we started this as some sort of game and amateur work. We stick to it, and basically, I remember the first start was because we were upset to be aware that all images were fractals. It seemed so ridiculous to us. So we said, okay, let's make image synthesis that takes into account all the ways to make images, and not this stupid idea that image should be scale invariant, self-similar, which was a huge restriction on the degrees of freedom that images have. Anyway, so we over the years we have contributed with other researchers. Let me mention them briefly. Bruno Galerne, who is now a professor at Orléans, Yann Gousseau, who is professor at Telecom, Agustin Salgado de la Nuez, who is a colleague of Luis, and also Nelson Monson Lopez, who is also a colleague of Luis at Las Palmas Gran Canaria. Well, so the starting point is that we all know that images can be acquired in many ways. But if we talk the point of view that they are constructed, like painted, for instance, or drawn, so we need to define the structure by which the image will be formed, okay? And so forms by themselves have structures. Images are constructed from forms, or from shapes by laws of compositions. And structures and laws of composition do not necessarily require figuration or animation. That means we are talking about, in general, abstract images. So then we have two questions. So the first question that arises is how to automatically create forms, texture, and image, which are abstract in the sense they are not imitating forms already seen. So where does this question comes from? It's everywhere. So it's central in decorative arts or in abstract arts. And I will show examples. So it's obviously a new question. The only thing that we can bring to it is perhaps to discuss technically. So to analyze technically all this aspect of abstract images, and to see, analyzing the techniques, if we can do other images, how, and what are the possible techniques at the end. As I said, our first starting point was looking at the first trials of mathematicians to make abstract images. So there is a famous dead leaf model by Matron in the 70s, which was not built to make art, but to model actually stone samples. Then this random tessellations was another model, mathematical model. And finally, last but not least, fractals, which were sometimes also called the iterated function systems, invented by Mandelbrot, Bentley, Demko. So it's a bit later, but it became also, this was very popular at the time. But all of these systems are very narrow in the fabrication law. Okay, it's a single law repeated all over scales. But let's say in parallel, there are digital art antecedents, many, and this goes on now. I mean, there is a lot of artists are trying to design images by computer. The first ones historically seems to be Georg Nies in 65, Michael Knoll, 64, composition with lines. This one is interesting because it was actually a pastiche of a Mondrian painting. And then it was proposed to many viewers to decide which one was the best. And this one won over the Mondrian. But really, they look almost similar. Also, John Maida. This is again composition. All of these compositions, as you see, have a structure. But what is the structure? This is what I want to discuss in a moment. In fact, to say it immediately, what is in common is that they are throwing shapes pseudo-randomly onto a surface. So it's quite close, in fact, to this model here that called the dead leaf model. So if we now say, okay, so what is the most general images that we can do? That means, so by most general, so mathematicians like to think in that way, that means a definition or an algorithm that would really be able to create any image in the world. So of course, if we say like this, we could just pick each pixel in the image, sort it randomly, and we could claim that at the end, our generator, or random generator, will certainly at some point make the Joconde, or at some point, we just wait. But this is like in Borges' library, you know, this library where all books are present. It's clear that you have to focus a bit on the synthesis law if you don't want to make only random noise images. So I will pass over quickly some examples of the problem. So, and the problem is clearly this. We have shapes. We start with shapes. Very often, actually, the shapes are fixed by the tool you are using, like pencil, how do you say, a brush, or a stab, or things like this. So, given anyway some shape generator, the question is how do you organize these shapes on the image? I have these. So this is an old problem because it probably started, for example, with the vases, because with vases you really need to cover them nicely, and so you have to figure out shapes that you can draw, and you have also to spread them, as you see, not at all randomly in those examples. So this is typical what people call decorative art. And this is another example of decorative art as a carpet. And there is a point in common between both, which is indeed something that one notices is that the repetition of shapes, the regularity, periodicity, symmetries of the shapes that are generally chosen, but not always. For instance, this Neolithic vase has quite interesting abstract shapes here that it's difficult to link to any figurative object. So going back to so perhaps the first to state the program in very explicitly, it's clearly it's Paul Klee, Kandinsky, etc. So these were theoreticians as well as artists, and so they decided that indeed they wanted to make a program to make images, to make paintings, and so the decision to go away from figurative shape led to a huge simplification, which is quite apparent here. If you look at the shapes that are being used in these paintings by Kandinsky, Delaunay, Hans Arp, van Doesburg, Mondrian, Pollock, you see that those are extremely simple shapes, geometric shapes, actually mathematical shapes. And then, because anyway, the number of degrees of freedom that you have already with simple shapes is infinite. So because of that, clearly, abstract art can allow itself to simplify completely the shapes. We'll go back on this. The last example is a bit different because it's using a different painting technique, which is splashing, so to say. And so here we don't have actually shapes, but still, in some sense, this is a shape of a splash. So assuming, we start with shapes, figurative or non-figurative, doesn't matter. So we start with shapes. So shapes are defined as subsets of the plane. And then if we want to make a random image, we could take these shapes, color them randomly, for instance. Then, so all shapes or colors or compositions are possible, but how do we do a composition? I think that this has been investigated at the same time by two schools that coexisted, which is the abstract painting school, so to say, and also the Gestalt school, which is a group of psychologists and physicists who decided to actually describe how images were perceived, but actually indirectly by describing how they were perceived, they also gave hints about their being built, even in the natural world. And so from here comes the terms I will be using. I will illustrate in a moment: occlusion, transparency, perspective, parallelism, good continuation, symmetry, convexity. So we'll see the first thing to explain these terms, we can comment actually on any abstract painting like this or this one. So we start with shapes, and when you are painting, you are superposing shapes upon shapes. So this is occlusion. But sometimes you want also to add shapes on top of shapes. Then you need a mechanism to define that. And this is what is called sometimes transparency, like here, or sometimes called also tessellation, because sometimes the shape you draw on is kind of creating new colors on both sides of its boundary. That this, for instance, this straight line here is actually dividing the shape and that were there before, so to say, and changing their colors in a different way on both sides. So this is what we call general tessellation. It's also here, apparent here, okay? So transparency and tessellation are clearly inventions, so to say, of abstract art, and they have had a lot of use because indeed it's a way to relate, in some causal way, shapes with former shapes. So this is very Kandinsky, and you see the technique between here and here is quite similar, except for the case that indeed in both cases we are using circles. So I can summarize in one slide the techniques that are used in cubism, in abstract art. And I would say that once you have shapes, you can, the question is how you spread them on the surface. So one way is to put them exclusively, so it's exclusion, the shapes don't intersect. They can also fall on top of each other like here. This is the Detlefs model by Matron. So it's occlusion, so we call it occlusion. They can also, as I said, create some effect on the former shapes, so to say, the shape that are, so to say, behind. And this is what we call tessellation. That means the change of colors, which is conditional to the former shapes. And then there are many others, not so many actually, but several others rules that can make a combination of shapes. First of all, you can organize them globally according to some geometric law, like perspective, like a vanishing point, or you can decide to make scales interact, like here, where you see that by some sort of scale causality, shapes of a certain sort are forced to be included in shapes of a different sort, and so on. This can be iterated. So this is not sort of generalization of fractals. Or finally, you can also use transparency like here, where in fact, this looks almost natural. It's like simulating that the objects are, the shapes, the objects are transparent to each other. So I've commented on that. So the next question you face when you want to make random images is that indeed you will. So one thing I forgot to say, perhaps has to be said somewhere here, that if you want to do abstract image synthesis, you don't want to do it by hand, by saying, oh, I will put this square here and this circle here. The obvious choice is to decide that everything will be done randomly. So with Louis, what we face as a problem is indeed to be able to randomly make a composition that has all these laws with all these parameters, because you have to pick randomly the sort of shape you take. You have to pick how you will spread them on the surface, how you will vary their size, and so on. So all this, in fact, is a program which is in fact quite simple, but that randomly picks between all these interaction laws between shapes and colors. And so immediately we face the problem of color, because we realize that if you do take random colors in the color cube, which means that red, green, and blue are computed completely randomly, you get simply horrible results. So I have to say that we decided very quickly that, in fact, so we explored the space of colors. So in fact, it has a structure, so we could make abstract space of colors, but very simply, more simply, we decided to simply borrow systematically colors from existing scenes, photographs, or paintings. for instance, this. So I will show you a series of examples and results. So on the right, you have the result of a program that randomly actually here subdivided. So it's a sort of tessellation. So it subdivided the plane. And each color here is picked randomly from this sample painting. What is really funny is that you recognize the painting. So we were very surprised to see that when we do that, we always could recognize the painting just from one such abstract composition made of it. So here the composition is made of rectangles that are random but oriented vertically or horizontally, and with transparency. But still, you see, and the colors are borrowed again from the painting of Pasimo on the left. Here, you have a composition made by rectangles with exclusion, so they exclude each other. And again, the colors are stolen from Kandinsky. And now I will show you more sophisticated examples. So if you ask me questions, I will tell more about the program, but in fact it is online, so the easiest way is to play with it. So I will show you some pics that we did of a generator that we have put online. The generator needs just one click. You click and you get an image. So the image I will show are actually the results of such clicks, but sometimes we took them again, like here. And to illustrate our point, I will explain the notion of style.
Jean-Michel, can you set parameters when you click, or these are preset parameters?
Yeah, actually, all parameters have some range, of course, but you can fix them by hand if you wish, because each one of these images I will be showing is actually associated with. It takes more or less one page. On the screen, you can see also. I can show it afterwards if you want. So each image is characterized by a list of values. Some values are logical. They say, for instance, took this palette, those are symbolic, they give the number of a palette, or they indicate that something has to be picked randomly, and some can be fixed by hand. But in fact, what we discovered is that in our exploration of what we can generate as abstract images is that we get a big diversity of images. So basically, what we prefer, our way of working is that we launch the algorithm with all parameters put at random values. And one thing is that since you have two sorts of choices in the algorithm, one chooses, so to say, what we call the style, and then you have extra parameters to fix, for instance, where the shapes will be put. The shapes are like in the dead leaf model, are put randomly, uniformly on the image. That means that if you start again the synthesis, you can get a different image with the shapes put differently and that has the same style. For instance, between this image here and that one, you have the same style, but not the same color palette. And if you like this image, you say, okay, I want to change the color palette, you change it. You could do it with exactly the same shapes at the same place, or you can do it by specifying if you want to play just with the palette or with the choice of shapes and so on. So in your online software, we can make all these choices as you wish. I will show it in a moment. And so once we had done that, at the beginning, so we started with relatively big and simple shapes. And with time, we went, and also with, say, the growth of the growth of the size of the screens, the fact that we can make so more and more computations in 20 seconds, which is our limit of patience. So we saw that we were able to create more and more complex structures. The surprising thing here is that The principles are exactly the same. What differs here is just the scale. Here, the image has many more, so to say, shapes and pixels, but it's exactly the same as the one I showed before. And so to illustrate what scale means, you see this image and this image have exactly the same style, same palette, only this is, let's say it's like a zoom in of the other one. It's the same image simulated with the same style, but with a different scale. And here, for instance, again, same here, same style as here, but different color palette. Again, exactly the same style as here, but a different color palette. So the fact that we can play independently with those parameters creates a huge set of possibilities, of course. So now I will go back to show some examples. So the point is that these examples are picked from a random generator that at some point we fixed. So it's a few years that we didn't change it. We are doing some other, what you are changing actually now is the shapes. We'll talk about that. So these are the latest compositions that come out from the fact that we are using more complex shapes. And I hope I will have time to explain briefly how we make the shapes. Because, so this, for instance, is the same as this, but not the same scale. Same style, not same shapes, not the same scale. Again, here, in this, it's exactly the same style, exactly the same color palette. So you see, this means that once you have a model that you like, you could make infinitely many variants of it. At some point, we thought that we would sell that to hotels, because big hotels have like 300 rooms, and you could make a different painting for each room for free. So they would pick the style, and then we would just multiply it. But we never tried to convince a hotel to do that for the time being. So again, so a change of scale. Here, from here to is a change of color palette. Here again, change of color palette. By the way, here you see that the creation is sophisticated because the color palette is actually changed on every piece of this, on every rectangle here. So I will go more quickly because just to show the slideshow very quickly that these are all variants of the same style. Okay? And these are like more, so let's call it as it is. All that I have shown until now, all this is texture. It's what in image processing we call texture. Why? Because basically there is one thing that you do here, which is that the shapes you put, the organization you put, could be shift right and left arbitrarily. The position of shapes is arbitrary in the image. So in fact, even it looks like very complex, it is a texture in the sense that it has an underlying translation invariance. So it's a landscape, a homogeneous landscape, and you see a tiny piece of it, of a big piece of it. When it's a big piece, it looks more like what we call normally texture, but this again is also a texture. So let me now go to, so here again the same. So just I was introducing to this that of course, then we can say, okay, an image is a scene, so it has objects. So what happens if we give up concession invariance? That means we will organize a scene. So the first thing we did to organize the scene is to create randomly. We allow sometimes to our random image to have a frame. And so on the boundary of the frame, the pattern here is also generated randomly. And the difference is that, of course, the frame is periodic, or more or less periodic with some variations. And in the middle, again, you can decide that the shapes you will organize will not be, again, always randomly. They will be picked much more individually, much more. So it's just enough to fix a small number of them, and then you get a scene. So what I will show now is a series of scenes, so to say, that have exactly the same code. That means you take the code into the computer, you tell run, it will create this, this, this. So every time it takes the shapes, it organizes them, it changes also the pattern of the frame every time. So it does to say a picture with a subject to say a sort of cubist picture, a simple cubist picture with a frame. So I've said enough on the making of the image because tomorrow I will have to show the online generator, but I will give you the link so you can play with it. It's completely simple. You go there, you click run, and you will see images, and you can also vary these images. But I will give just a very simple introduction to the other side of the problem, which is shapes. So as I told you, we did as the abstract painters at the beginning. We just tried with very simple shapes like circles, rectangles, parallelograms, and so on. And at some point, we said, okay, but there is a mathematical theory of shape. It was actually of shape structure, I mean, because obviously you can say that a shape is just any subset of the plane. It would be the set theory viewpoint, but then all your shapes would look like a random line, random noise, like say black beans on the background of white beans randomly spread. So you don't get shapes. If you want to have a shape, you need, let's talk about connected shapes, about shapes that do have some sort of organization. So for these shapes, Bloom created the notion of what he called the medial axis transform, which was a way to associate to each shape its structure. And this shape from the point of view of Bloom's theory is a graph, actually, is a graph. So it's a set of curves, which are the set of centers of internal disks that are bitangent to the shape's boundary, together with the radius of this disk. So what that means is that you can define a shape as a tree, so to say, a tree or a graph connecting points by curves. But at each point of the tree, you do have a radius. So this is very interesting because it's easy to create random graphs. It's easy to create random radius functions, smooth, of course. And so the set of centers is called the skeleton of the shape. And the radii are, so to say, the thickness of the shape at each point. And so let me illustrate it immediately that by the fact that we tried to translate this definition into something that is computationally feasible. So to make it computationally feasible, you need just to be able to create a random graph, like here, this is a tree, you see. So you need to pick, you have to pick, so these the dots here, the black dots are the nodes of the graph. They are connected by edges, and the skeleton of the shape is the union of these segments. And so then you need also to fix a function for the radii. And what we did to make a very quick shape generator is that we only fix the radius from the nodes. And then we use a very nice computer graphic tool, Bezier curves, to deduce the contour from this skeleton together with the disks. And so in that way, in principle, we could be able to generate, I will skip the details. So we could be able to regenerate any shape. But of course, we saw quickly that we needed to create shape styles too. But some are completely general. So in fact, the style 6 is general, but we also created some more special styles like stars, spirals. So the ones that have some sort of simplification, but more than anything, we created symmetric and periodic shapes. So these two styles that in fact are allowed to do, so to say, decorative arts, because decorative arts is really characterized by these repetition patterns. And so I will skip. So to illustrate what it gives, I will show this because this I did, I had to be patient to do that. I took our shape generator and I picked all shapes that have genus 0. That means they have no hole, okay? As they appear, okay? Because, and I discarded the complex ones. I just kept the simplest ones that had not too many corners, so to say. And just because I wanted to check if our random generator would retrieve somehow existing shapes. And this is what I found. So these are the 97. Then I lost patience because there were many repetitions and but funnily, so this is what you get with the 97 first shapes or generator, first shapes with genus 0 and not too complex. And yes, indeed, you see, or at least for the simple shapes, you somehow retrieve classic shapes, so to say, shapes you might recognize, no? Of course, the simplest one has circles, but many could be used as logos and so on. So this is what we saw when selecting the simplest ones. And then but of course, when you start allowing for more complex graphs, more complex interaction rules between the branches, this is what you get. You can get, it becomes infinite. And the bad point of infinity is that you cannot explore infinity. So I'm showing here a few examples of styles, of shapes that we can generate, and many others we will never find. I mean, you will never find a bunch of roses, because that we need really to steer the algorithm. But anyway, so there is a big diversity. Here are examples where you can see here you have some symmetry that is applied randomly. So this is a sort of Art Deco shape, to say. And then applying and also the notion of styles, the style emerged again because every shape is defined by certain characteristics of the graph, like it has certain depth, certain number of edges, so on. And so some rules about whether the range can meet or not, some rules about symmetry. So once you have fixed a style, you can, as I did for images, you can repeat this style. And so if you repeat this style, since it has random choice about the number, for instance, of bifurcations at each node and so on. This is, for instance, the first one was this one. And when you click repeat, this is the list of shapes that come out they have more or less the same texture, the same aspect. So it's the same style of shape. Surprisingly, this one came out. I don't know if it was a bug or because it doesn't seem to have the right number of nodes, but anyway, but maybe one of the parameters made it so simple. So anyway, so this is, so one can create with a random generator, not just shapes, or not just image, one can create styles. This is what I find was our unique contribution, because otherwise there's nothing original in what I have said. And actually all images you have seen and shapes you have seen are not original. But the fact that you can vary like this is surprising. So I will show some a few examples. This is another example of style. So here we said, okay, this looks like a letter, so let's make an alphabet. Okay. So this would be an alphabet in the sense that all these letters, so to say, have the same style as the first one. They are all different because at this stage already, with you see, you have enough random choices that the probability that two will come out to be exactly the same is already quite small. And this is a problem. The set of shapes, the set of images is infinite. So now I'm ready to answer your questions. I don't know if I have time left, but anyway, if I have 1 minute left, I can just show the site where we.
Yeah, that would be great. Yeah, I mean, maybe we could even take questions while you're looking for the site, Jean-Michel.
Excuse me?
Maybe we can take questions while you're looking for the site.
Yeah, sure. Anyway, you can go yourself. Maybe it's better if you go yourself. If you have a screen too. So the site is called GMNLA. In fact, it's our initials, GM is me, and LA is Luis Alvarez, and N in the middle, .com. But yes, well, I will show you this page also on screen. Meanwhile, you can please ask me questions if you have. I will be very happy if you have any comment, any advice.
Oh, it's really fascinating. Questions. I mean, I could start, Jean-Michel. So did you also think about the inverse problem in the sense that, let's say I give you a Kandinsky and you extract the style and, I mean, the color palette you have shown, right? So the color palette you have shown, but could you extract more, the scale and...
Yes, yes, okay, so the inverse problem. So actually, we are advancing on the shape inverse problem, which is to create, from a given shape, to create its skeleton, simplify it, and recreate and create the style of it. This, I think, will work. It's in work in progress. So we do have a good skeleton algorithm. So we know. So soon we have a generator of shapes that can take an existing shape and extract its structure, and then so create its style. So be able to vary it. Okay? This was one of the goals we had. But you're asking the same for images. So for images, well, even a simple painting like the one by Kandinsky that I showed is not so simple. So to recreate its structure visually, we can say, oh, okay, here I can make a comment of it like I would do in front of image processing students. Tell them, okay, what you see here is 10 circles. Okay, and this is a technique by which they are superposed. Here you have transparency. Here you have a change of scale. Here you have a perspective because these circles are shrinking in some directions. So I can comment it technically. And of course, we can also comment on the color perhaps. But this is based on our perception. I don't think, maybe no, with neural networks, we might teach indeed a neural network to make some sort of style from simple paintings, perhaps, yes. Perhaps
but in what you are doing is more interpretable, right? Because you really have these are different variables
yes.
in your algorithm, right? So the shapes and the scale and the color palette and so on. I mean, you could have a neural network autoencoder that somehow generates similar images then.
Yeah.
But or generator or something like this. But it's still different, no? It's very different actually.
Yes. Well, in fact, yeah. So we hope after the shapes we can deal with images too. In fact, as you know, in art there is a novel. While we were doing that, people have not been inactive. So you know that now there is a big progress in neural networks. And in fact, neural networks are by now able to reproduce very accurately any texture. This is a progress that was really recent. So it's 5 years ago, a paper by Gattis and others, that you give it any, say, piece of wood or any texture, and you can reproduce a texture that looks very similar. It's a huge neural network. But of course, it's not, I mean, you know that people in AI have created all sorts of new terms that are like projects to, you know, like they call it, like, for instance, structure, transfer learning, few shots learning. So all sorts of terms that in fact indicate that they see that AI is not intelligent. They would like it to be intelligent. One of these terms is explainable AI. So when something works, can we explain what the network does? And this is the problem with Gattis algorithm. the best explanation of it is actually the analysis made before by psychophysicists about the moments of texture, but there is no explanation except, wow, it works. So in that sense, one can reproduce, probably, one be able to reproduce if you have enough examples. But even in the case of a texture with a single example, you can reproduce a similar texture.
Yeah.
In the case of paintings, I'm not sure you have enough on Kandinsky to create a new Kandinsky, because the attempts I've seen of this kind were relatively unconvincing. I mean, unconvincing in the sense that the papers pretending that are making lots of tweaks and to make it like it worked, but in fact it's like copying. I mean, it's not automatic at all.
Yes, 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 yes.
Just before I stop completely, so let me show you, because you asked for this, you asked for the code. So this is the code of one of the images I've shown. Okay, so typically like one page, and you see terms like rotation, palette, depth of the node. You see, so it's in fact it's all a graph with values also for images, and you have also rendering choice. This you can see here tessellation, okay, light, transparency, okay, border thick, okay, inclusion further, so it creates interaction between shapes and their subshapes that are contained in it. Exclusion of borders in the same mode. You see, so all these choices are made randomly.
Yeah.
So this is why we are in a huge probability space. Of course, much smaller than the probability space of all images, but more restricted to what humans consider images. That means that this combination of shades, etc.
Yeah, this is really fascinating.
If I may, I have one quick question. Thanks a lot for the nice talk. I was wondering if you can change the metric in the medial axis transform in order, I don't know, to create different shapes, possibly without smooth borders, or I don't know, changing from L2 to L1.
You mean distance from a shape to another shape? Is what you mean?
I mean, instead of looking at the center of circles, looking at the center of squares and changing the metric inside this transform to create different smoothness in the border.
Yeah, we do. Yeah, actually.
Okay.
Yeah, we do. Actually, if you look, okay, so I have to show to that. Let me go back to the, 1 second. Yeah, let me go back to the, there is an online demo creating shapes. So I had no time to show it, but I can show the one.
So you have this level of flexibility in choosing the metric. For,
in fact, there is a smoothness parameter, and depending on the smoothness parameter, you get more or less. You can vary the shape, so to say.
Because I would assume that your atom element you stated is a circle, because you have the metric, which is well too. But if you change it, your atom would be the square, or I don't know, ellipse, or.
Yeah, precisely. Yes, indeed. Somehow it's a bit shown here. Here, from this triangle to this object is the smoothness. Okay.
Okay.
So yeah. So in fact, this is also randomly chosen again.
Super. Thanks.
So I think there is a lot of discussion that we could have continuing. Maybe, I don't know, Jean-Michel, if you can stay on until after Pierluigi's talk, because we have a coffee break then, and we could.
Yeah, sure. I don't move. Don't worry.
Okay, excellent, perfect. Okay, so then I suggest we thank Jean-Michel again very much for the talk. Thank you very much.
Thank you.